in your home, and you may see that your calculation will be matched with this expression or not. Okay. So if the expression is getting matched with this value, or sorry, with your calculation, then that will be okay. It's fine. So if not matched, then there should be a kind of problem. Okay. Okay. So finally, we will get the expression of this function ft into the Fourier series expansion, and that will look like this: twice k plus 1 by 4, twice k plus 1 by 4. Actually, if we simplify this expression, this will be twice k plus 1 by 2. If this twice k plus 1 by 2 is divided by 2, that will be twice k plus 1 by 4, plus summation n is equal to 1 to infinity 1 by n square pi square into minus 1 whole to the power n minus 1 cosine of n by t. That is the expression of an, and this is the expression of bn into sine of n by t. Fine. So this is the expression of Fourier series expression of the function ft is equal to k when t is lying between 0 and 1, and is equal to t when t is lying between, sorry, first one, the first interval is 0 to, sorry, minus 1 to 0, and the second interval is 0 to 1. Okay. Pardon. So this is the thing. The fundamental frequency is pi. Yes, what I have said earlier, at 0 the function is discontinuous, right? So if we look into the pictorial diagram of this function, then you may see there should be a discontinuity at the point t is equal to 0. There should be a jump between at the point t is equal to 0. Fine. So this is what I am trying to say here. So yes, this is the remarks actually. The fundamental frequency is pi, and at 0 the function is discontinuous, right? So yeah, this is the thing. This is the catch of this of the today's lecture. Is the what would be the value of the function at t is equal to 0 again? Then you may see the function of t is equal to 0 minus the value is equal to k, and the function of t is equal to 0 plus the value is equal to 0. Okay, so I have told this earlier that at t is equal to 0, if we see this figure, at t is equal to 0 minus the value is k, at t is equal to 0 plus the value is 0. Therefore, if we take the average of f0 minus and 0 plus, then the value would be k plus 0 by 2, that would be k by 2. Okay, so we can say that at x is equal to 0 point, at x is equal to 0, I am repeating again, at x is equal to 0 point, the functional value of ft will be converged or will convert this to what? Will convert this to k is equal to 2. Okay, so at this value the functional value will be converged, or the functional value converges to k is equal to 2 at the point of discontinuity. Okay, so at the point of discontinuity the functional value now converges to the average value of f is equal to 0 minus and f is equal to 0 plus. That is k by 2. Okay, so this is the thing. Yes.
So the function is a convergent function. That is why the function is converged to the average.
Okay. Yes, the function is convergent. Actually, if we talk about any other point except t is equal to 0. Okay. If we consider all other points except t is equal to 0, or you may say except the point of discontinuity, then everywhere the function converges. Actually, from minus 1 to 0, the function value converges to k. Or 0 to 1, the value converges to this function t, fine. Actually, and similarly, at the point of discontinuity, I mean here the discontinuous point is t is equal to 0, right?
Yes.
Discontinuous point. So what will be the value, or what at which value the function will be converged at the point t is equal to 0, t the point of discontinuity, so we cannot determine the value actually, right?
Yes.
So mathematically it has been proved that at the point t is equal to 0, or at the point of discontinuity, the function will be converges to the average of the f is equal to 0 minus and f is equal to 0 plus. Okay. So this is the thing. Actually, mathematically, you may prove also. Okay, this proof is has been depicted in textbook, any kind of textbook. You may see there. Okay. That means at the point of discontinuity, the function converges to a by 2.
So the x equal to 0, the point is called the point of intersection or point of discontinuity.
Yes. At the point t is equal to 0, the function is discontinuous, right? Yes. So if we're trying to get the convergency, I mean, if we try to actually, if we try to see the convergence of the function, okay, then what we will see at the continuous time interval, we will see the function converges to the functional value. For -1 to 0, the function converges to k. For the interval 0 to 1, obviously open interval, not closed interval, the functional value converges to t. And for the point of discontinuity, at the point t is equal to 0, because actually at the point t is equal to 0, the function is discontinuous. Okay, actually, if we take t is equal to 0 minus, then the functional value is k, right? And if t is equal to 0 plus, the functional value 0. Okay, if we imagine an imaginary line segment, okay, if we imagine an imaginary line segment here, okay, here at here, then physically the mid amplitude will be, if we imagine that, okay, then the mid amplitude will be the value, right? This is the imagination actually. So, but mathematically it can be proved, I ensure you. So basically this is our we can physically implement this function, that at t is equal to 0 point, the functional value converges to f0 minus plus f0 plus divided by 2. Okay. If we talk about t is equal to 1, actually if we go upward, then you may see at the point t is equal to 1, this is also the point of discontinuity, right? At the point, this is also a point of discontinuity. So the convergence will be takes place at, actually if we talk about the convergence, then at the point t is equal to 1, the value will be f of 1 minus plus f of 1 plus divided by 2. At the point t is equal to 2, the functional value converges to f is equal to, function of 2 minus plus function of 2 plus divided by 2. Right? This is the thing. Actually, if we talk about t is equal to 2 point, we will also see the functional value converges to a plus 0 by 2, that means k by 2, right? Is it right? At every point of discontinuity, we will get the value of convergence will be k by 2. Okay, the functional value will be converges at k by 2 for this particular example. Okay. Okay, now yes, ft is the function of time, the signal, the period is capital T. The Fourier expansion is a0 by 2 plus summation n is equal to 1 to infinity and this expression, right? And where omega 0 is equal to twice pi by t, okay, or twice pi f. So this we have seen earlier, actually in our previous class. And an and bn is defined as 2it integration minus t by 2 to t by 2 ft cosine of this function and sine of this function. Okay, so this is the expression of an and bn. So the Fourier coefficients are a real valued function, So here cosine term is here and sine term is here. So this total expressions of an and bn are a real valued function. Okay, a real valued function. So we may take an example here of the path of satellite. Okay, if we talk about a geostationary or a geosynchronous satellite, their path in general circular. Okay, so if we take the radius r and if we take the angle is theta, then zt is equal to xt plus iyt is equal to rt to the power I theta t, where xt is equal to r cosine of theta and y is equal to r sine of theta. Okay, so this is we have started earlier when we have talked about the complex signal. Okay, the complex signal. The example was e to the power I theta, right? That is equal to cosine of theta plus I sine theta. Okay, that is the mixed signal. I mean, that is the complex like signal. The cosine theta and sine theta belongs to the real number set. But if we talk about the combination of these two real numbers, including the I, where I is the root over of square root of -1, then we will see z is equal to x plus iy, that is equal to cosine of theta plus I sine theta. The combination, this combination is called the complex signal, complex function. Okay, so this time now. Okay, so if we talk about the complex signal, we are familiar with this formula: cosine of n omega 0 t, e to the power I theta is equal to cos theta plus I sine theta, e to the power minus I theta is equal to cos theta minus I sine theta. If we calculate this type of expression, if we eliminate the sine term, then the cosine of theta will be e to the power I n omega 0 t plus e to the power minus I n omega 0 t divided by 2. Okay, I mean the cosine of n omega 0 t will be this expression. Similarly, in case of your sine of n omega 0 t, the expression will be this: e to the power this I theta minus e to the minus I theta by twice I. So now the Fourier series expression was ft is equal to a0 by t plus summation n is equal to 1 to infinity an. If we substitute the cosine n omega 0 t, cosine n omega 0 t by this expression e to the power I n omega 0 t plus e to the minus I omega 0 t by 2 plus bn into this expression. Fine. So that would be a0 by 2 plus summation n is equal to 1 to infinity e to the power I n omega 0 t, that will be common, and we will get an by 2 minus I bn by 2 closing of second bracket plus this expression. Fine. So we will get this total expression, and this form is complex in nature. Okay, Okay, so now what we will see, uh, n is equal to 1 to infinity, and this one a0 by 2. Now ft is equal to, if we talk about a0 by 2, that means a0 minus ib0 by 2. If we substitute a0 by 2 here, then we will see a0 by 2 minus b0 by 2, as b0 is equal to 0. We can write here like this, a0 minus ib0 by 2. Okay, b0 is equal to 0 here actually. Okay, b0 is equal to 0 here. So a0 minus 0 by 2, that means it can be written as a0 minus ib0 by 2 plus this expression n is equal to 1 to infinity, and blah blah, this is all. So e to the power I n omega 0 t n minus I p n by 2, this one, then that would be equal to n is equal to 0 to infinity e to the power I n omega 0 t into n minus I p n by 2, but the lower limit is n is equal to 0 and the upper limit is infinity. For this expression, the lower limit is 1 and upper limit is infinity. Okay, if you cannot understand, you may ask me. Okay, you may do it yourself, and if you face any kind of difficulty, please ask me in my further lecture, in my future lecture. Now this is an imagination. That means we may take Cn is equal to an minus ibn by 2 and C minus n is equal to an plus ibn by 2. If we substitute this whole expression by Cn and Cn minus 1, that would be looking like this, and ft is equal to summation n is equal to 0 to infinity Cn e to the power this expression, and n is equal to 1 to this expression. Finally, we have come up into this formula minus infinity plus infinity Cn e to the power in omega 0 t. Okay, so this is the final expression which we have got from the Fourier series expansion, and this is called the Fourier series expansion in complex form, where Cn is equal to an minus ibn by 2. Okay, and Cn is equal to 1 by 2, 2 by t minus t by 2, 2 plus t by 2 ft cosine of this one plus I 2 by t, and this expression, and finally we have got 1 by t minus t by 2 t by t ft e to the power minus I n omega 0 t dt. Okay, so here unlike your previous Fourier series expansion where an and bn were the real coefficients, now we will see the Cn is the Fourier coefficient, but the Cn, the Fourier coefficient, is the complex one. Okay, because this complex term is here. So therefore we have got that the ft, the Fourier series expansion, can be expressed as this formulation minus infinity plus infinity Cn e to the power I n omega 0 t, where Cn is equal to minus 1 by t, the time period, minus t by 2 to t by 2 ft e to the power minus I n omega 0 t. Okay, this is the difference between our previous Fourier series expansion and this time Fourier series expansion. Okay, the real valued function and the complex valued function. Okay, so this is all for today's class. Let me summarize. So in this class, first we have talked about a typical example where our functional value ft is equal to k for minus 1 less than t is less than 0 and is equal to t when 0 is less than t is less than 1. And we have found out the Fourier series expansion, the an and bn. Then finally we have come up into the simple formulation of the Fourier series, which is twice k plus 1 by 4 and this one. And the common confusion is here that what would be the value of the point of discontinuity. Actually, what I mean, at the point of discontinuity, at how much value the function will be converged. Okay, so here we have seen that at the point of discontinuity, the functional value converged to a by 2, okay, which is the average of the function of 0 minus and function of 0 plus values. Okay. And then now we have discussed about the complex valued Fourier series expression or complex valued Fourier series expansion. Okay. And we have decomposed the cosine term and sine term into exponential function. Okay. Then we have calculated and finally we have seen that function of t is equal to minus infinity to plus infinity, this expression where Cn is written as 1 by t minus t by 2 plus t by 2 ft to the power minus I in omega 0 t. Okay. So this is the Fourier expansion with complex valued functions. So this is all from me for today's class. If you have any question, please ask me. Thank you very much. Okay, do you have any question or I shall leave?
Sir,
Yes.
sir, the complex signal or complex value function obey the digit condition.
Okay. Yes. Yes, the Dirichlet condition should be satisfied. Okay.
Okay, sir.
Okay, thank you very much.
Thank you, sir.
Thank you, sir.
Thank you, sir.
I am leaving.
Boom.